Hello friends, Mr. Burrell here. We're in the last section of Unit 4. We're almost completely done talking about polynomial functions. It's a bittersweet farewell for me, but we're going to end off talking about this with the sum, and difference of cubes. A little bit earlier in this unit, we talked about a special factoring situation called difference of squares, and kind of a unique pattern that happens when we have a quadratic equation that's a difference of squares, two terms when both of the terms are perfect squares. So today we're going to talk about a special factoring situation that happens when we have two terms adding or subtracting together that are perfect cubes, and how we can go about factoring or breaking down those equations. So by the end of this lesson, we'll be able to factor using a sum of cubes formula and factor using a difference of cubes formula. And one of the big reasons we cover this in this unit is because almost always a question associated with this pops up on the ACT. So I want to make you aware of this pattern, this relationship that exists, in case you do happen to see it on the ACT. Okay, so here are kind of the formulas, the patterns. So if I have a sum of cubes, or in other words, if I have two terms added together that are both perfect cubes, meaning that if I multiply a times a, something by itself 3 times, I get this a cubed, and b times b is b cubed. If I have two perfect cubes added together, then I could factor that out like this. A plus b times a squared minus ab plus b squared. So I take whatever a is plus whatever b is, and then I multiply that by a squared minus a times b plus b squared. Note that in this formula, this sign is positive, this sign is the opposite of what this sign was, and this sign was the same as what this sign was. So I have this kind of guide in your guided notes where this sign is the same sign, this is the opposite sign, and this sign is always positive. The other formula here that we have is a difference of cubes. So when I'm subtracting two perfect cubes, and you'll notice that these formulas, they factor out almost the exact same way. All of these terms are almost exactly the same, with the exception of some of the signs. So again, this is the same sign, this is the opposite sign, and this is always positive. So how that changes when I have the difference of cubes, this sign right here is now negative instead of positive, and this sign right here is now positive instead of negative. So you can keep this handy for reference. You can use this section of your notes. I'm not going to prohibit it from you. In fact, I would use it so you can have these formulas available. But this is kind of a handy pattern that pops up when I am trying to factor the difference of a set of perfect cubes or the sum of a set of perfect cubes. So let's see how this will work out in a problem. So the instructions might say factor each polynomial using either a sum or a difference of cubes. Okay, so let me go back here. So here you'll notice I have a sum of cubes. How do I know that? Well, I have two terms. They're being added together, and they're both perfect cubes, meaning that if I were to factor these out, u cubed and 27, they would both be perfect cubes. So u cubed I could factor out to be u times u times u. Three terms that are exactly the same. If I were to factor out 27, I'd get 3 times 9, and then 3 times 3. So 27 is equivalent to 3 times 3 times 3. One number multiplied by itself 3 times. So those are both perfect cubes, u cubed plus 27. So in my sum of cubes formula, I had a cubed plus b cubed. So a would be equal to u, and b would be equal to 3. So a is equal to u, b is equal to 3, like I just said. So if a is equal to u and b is equal to 3, I'm going to go ahead and plug those values, u and 3, into my sum of cubes formula. A cubed plus b cubed is equal to a plus b times a squared minus ab plus b squared. So that was the formula for sum of cubes. So now I'm just going to replace everything that says a with u and everything that says b with 3. So you see I've already done this for you here. So u cubed plus 27 is equal to u plus 3, a plus b, times a squared minus a times b plus b squared. So a squared would be u squared. A times b is 3 times u. And b squared is 3 squared, which is 9. So that's the factored form of that sum of cubes. So that's how I would factor that out. And now you notice that u squared minus 3u plus 9, if I wanted to solve that, if I wanted to finish solving this, this is a quadratic equation. So I could use the quadratic formula to go ahead and finish solving that part. So now it's something that I'm familiar with. I know how to solve quadratic equations. So I just went from the sum of cubes into this equation that now I know how to go about finishing solving. So that's an example of a sum of cubes. So that one was pretty straightforward. Let's look at another couple of examples that might look a little bit different. So here I have the example negative 27x to the fourth plus 64x. Okay, first thing I want to see, I need to get this into a form of either a cubed plus b cubed or a cubed minus b cubed. And we typically want the x cubed, the variable part, first. Okay. So first thing we're going to do, before we do anything, we should take out and see if there's a greatest common factor. So between both of these terms, do I have a greatest common factor? So if I break down 27, I get 9 times 3, and then 3 times 3. If I break down 64, I get 8 times 8, and then in each of these I get 4 times 2, 4 times 2, 2 times 2, 2 times 2. So I don't have any common factors between the numbers. Now, do I have any greatest common factors between the variables? Yes, I do. I have x to the fourth here and x here, so I can take out an x from both of those terms. And I'm also, because I don't want my first term to be negative, up here I don't want my first term to be negative, I'm also going to take out a negative. So when I take a negative x out of each of those terms, I'm left with a positive 27x cubed. Took one x out of there. Minus, because a negative times a negative is a positive, minus 64. So when I took out a greatest common factor, I'm left with 27x cubed minus 64. Now this, I'm going to ignore the negative x for a second. If I have 27x cubed minus 64, this first term is x cubed. This is starting to look really similar to a difference of cubes problem. So if this term is a perfect cube and this term is a perfect cube, I'll be able to use my difference of cubes formula. A cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. I'll be able to plug those perfect cubes into this formula. So the cube root of 27 we already identified was 3. So a, in this case, my a term is going to be 3x. Because the cube root of 27 is 3, the cube root of x cubed is x. My b term is going to be the cube root of 64. We'll notice here I have 2 2's, 2 2's. I have 3 different pairs of 2's. 2 times 2 is 4. So 4 times 4 times 4 is 64. So 64 is a perfect cube too. Namely, the cube root of 64 is 4. Well, that's handy. That's really convenient. Now I can use the difference of cubes formula in order to factor that expression. So a is 3x, b is 4. I'm going to plug those in here. So I have 3. So a cubed minus b cubed, or 27x cubed minus 64, is equal to a, which is 3x, minus b, which is 4. Then a squared, 3x squared will be 9x squared. 3 squared is 9. X squared is x squared. Plus a times b, which is 3x times 4. So this was 3x squared. This is a times b, which is 3x times 4, which is 12x. Plus b squared, which is 4 squared, which is 16. So that is the factored version of that difference of cubes. 3x minus 4 times 9x squared plus 12x plus 16. And now if I wanted to, this is a quadratic equation now, so I could use the quadratic formula to solve that part. If I wanted to finish solving and factoring this, I would be able to solve this quadratic part using the quadratic formula. So notice again when I'm looking at the difference of cubes formula, these signs better be the same, these signs better be opposite, and this sign better always be positive. Okay. Hopefully you have that down. I'm going to erase this now. Speak now or forever hold your peace. I'm going to erase this so I have some room for problem number 2 here. So I have 8 minus x cubed. So I want, first of all, I want the variable part first most of the time. So I'm going to switch these spots and write this as negative x cubed plus 8, because I want the variable part first. Well, now I want it to be in one of these forms, so the first term needs to be positive. So when I'm looking at a greatest common factor, I'm going to take a negative out of both of these terms, so I'm left with x cubed minus 8. X cubed minus 8. Well, now this x cubed minus 8 business, if x cubed and 8 are both perfect cubes, then I can use my difference of cubes formula in order to factor that out. Well, 8, when I factor that out, I get 4 times 2, and then 2 times 2, 1, 2, 3. 8 indeed is a perfect cube. All these numbers you can also double check in a calculator. You can use the cube root function and double check that they are actually perfect cubes. And then x cubed will always be a perfect cube. So if I go over here and I have x cubed minus 8, a is going to be equal to x, because that's the cube root of x cubed. B is going to be equal to 2, because that's the cube root of 8. So if I fill in all my terms here, x cubed minus 8 is going to be equal to x minus 2 times x squared plus 2x plus 2 squared is 4. So I get x cubed minus 8 being equal to x minus 2 times x squared plus 2x plus 4. And then if I wanted to finish solving this, now this is a quadratic, and that's something I know how to deal with. I have a whole arsenal of tools that I can use for that quadratic function, so I can finish solving this after I've changed it from a difference of cubes into a binomial times by a quadratic. So that's the difference of cubes. That was kind of a shorter video. Again, we bring this up because it does pop up fairly often on the ACT, and we want you to be prepared for that. So go ahead and check yourself at the end of this video. This is what I hope that you're able to accomplish. I hope that you're able to factor using a sum of cubes formula and factor using a difference of cubes formula. So I would very much keep this page with those formulas, the sum and difference of cubes formulas on them, and keep them for reference. But I hope that was helpful. Please reach out to me if you have any questions whatsoever, and I hope that you enjoyed that as much as I did.